Most people can tell you their street address, their city, their country, and if they are paying attention in school, maybe even the name of the galaxy they live in. But ask them to go one level higher, one step further out, and almost everyone goes quiet. There is a structure above the galaxy. There is a structure above the galaxy cluster. There is an address most people have never been given, and it belongs to a place so enormous that the number of galaxies inside it runs to roughly 100,000. We live inside it right now. Most people have never heard its name. That silence matters. It is not a gap in trivia. It is a gap in something more basic, the question of where, exactly, you are. Humans have spent thousands of years getting better at answering that question. We mapped the continents. We tracked the planets. We measured the distance to the sun, to nearby stars, to the edge of our own galaxy. Every generation pushed the answer a little further out. And then for a long stretch, the answer stalled. The galaxy was as far as most people got, and the Milky Way became the edge of the mental map. Beyond it, in this informal accounting, was just space, undifferentiated, unmapped, vast. The truth is stranger and more structured than that. The universe at its largest scales is not a smooth, even fog of galaxies scattered randomly in every direction. It has bones. It has architecture. Galaxies cluster together. Clusters gather into superclusters. Superclusters are themselves embedded in a web of filaments and voids, stretching across hundreds of millions of light years. This structure exists whether or not we know about it, and we are inside it. The question was never whether there was a larger address. The question was whether anyone would ever figure out what it was. In 2014, a team of astronomers did. What they published that year was not just a new measurement or a refined catalogue. It was a map of something that had never been mapped before, the full supercluster that contains the Milky Way, defined for the first time with a clear boundary, a coherent shape, and a name. The structure stretches 520 million light-years across. Its total mass runs to something like 100 quadrillion suns. It holds roughly 100,000 large galaxies inside it, all of them flowing, slowly and gravitationally, toward a common center. And almost nobody outside of astronomy has heard of it. The name comes from Hawaiian. The team behind the discovery was based at the University of Hawaii, and when the time came to name the structure, they consulted with Hawaiian language experts rather than reaching for the usual Latin or Greek. The word they settled on is Laniakea. Lani means heaven or sky. Akea means spacious, open, immeasurable. Together the phrase means something close to immense heaven. There is something right about that. Polynesian navigators once crossed the open Pacific with no instruments and no landmarks, reading the sky to find where they were in the world. The name given to our supercluster reaches back to those same navigators, and it carries that same orientation, looking up to understand your place. Most people have a cosmic address they have never been told. Street, city, country, planet, solar system, galaxy, galaxy cluster, supercluster. That last entry is the missing one. That is the level where the address has, until recently, been blank. For decades, astronomers thought the Virgo Supercluster was the best answer, a structure about 100 million light-years across that the Milky Way sat on the edge of. But that picture was incomplete. The Virgo Supercluster turned out to be a small piece of something much larger. What replaced it is deeper, wider, stranger, and harder to picture. It took a new way of thinking about the problem entirely, not just pointing telescopes but rethinking what a supercluster even is, before anyone could see it clearly. That discovery, how it was made, what it revealed about the structure we are embedded in, and what it means for the question of where you are. That is what the rest of this is about. The name is Laniakea, and understanding what it is changes everything about how you think about where you are. For decades, if you asked an astronomer where the Milky Way sat in the largest known structure, the answer was the Virgo Supercluster. That was the official answer. That was what the textbooks said. And for a long time, it felt like enough. To understand why that answer seemed satisfying, you have to walk through the hierarchy that astronomers had assembled piece by piece over the 20th century. Start at the bottom. Earth orbits the Sun. The Sun is one star among several hundred billion in the Milky Way. The Milky Way, a barred spiral galaxy roughly 100,000 light-years across, belongs to a small cluster of galaxies called the Local Group. The Local Group contains around 80 galaxies in total, most of them small and dim, gravitationally bound to each other and to the two dominant members, the Milky Way and the Andromeda Galaxy. That cluster spans roughly 10 million light-years. Beyond the Local Group, things get larger, much larger. The Virgo Supercluster was the next rung on that ladder. It stretched roughly 100 million light-years across, an enormous region of space containing thousands of galaxies organized into smaller clusters and groups, all loosely associated around a gravitational center. At that center sat the Virgo cluster itself, one of the nearest large galaxy clusters to us, holding several thousand galaxies packed into a region roughly 8 million light-years wide. The Local Group sat on the outer edge of this structure, a minor outpost well away from the dense central regions. That was the address. That was the picture. The man most responsible for assembling it was a French-American astronomer named Gérard de Vaucouleurs. Working in the 1950s, de Vaucouleurs noticed something that had been hiding in plain sight. When he plotted the positions of nearby galaxies across the sky, they weren't scattered randomly. They clustered preferentially along a flattened plane, a great disk of galaxies tilted roughly 6 degrees relative to the celestial equator. He called this the Local Supercluster. Other astronomers were skeptical. The concept of superclusters, enormous structures containing multiple clusters of galaxies, was not universally accepted at the time. Some researchers argued that what de Vaucouleurs was seeing was just a statistical accident, a coincidence in the distribution of nearby galaxies rather than a genuine physical structure. The debate went on for decades. Gradually, as observations improved and galaxy catalogues grew larger, the reality of the Local Supercluster became harder to dismiss. By the 1980s, most astronomers had accepted that de Vaucouleurs had been right. The Virgo Supercluster was real, and once it was accepted, the picture felt remarkably complete. You had a clean hierarchy. Planets orbited stars, stars gathered in galaxies, galaxies gathered in clusters, clusters gathered in superclusters. The universe was organized, nested, logical. The Virgo Supercluster was the top of that nesting, the largest box that contained our box, and it had a sensible size, about 100 million light-years, and a sensible shape. It was centered on a visible, well-studied cluster of galaxies. You could point to it on a map. Cosmologically speaking, the address problem seemed solved. Then the data started behaving strangely. The universe is expanding. Edwin Hubble established this in 1929, and by the second half of the 20th century, it was one of the most thoroughly confirmed facts in all of science. Galaxies are receding from us and from each other at speeds proportional to their distances. The further away a galaxy is, the faster it appears to move away. This is not galaxies moving through space so much as space itself stretching, carrying galaxies along with it. If you know a galaxy's recession speed, you can calculate its distance. This relationship, called the Hubble flow, forms the backbone of how astronomers measure the large-scale universe. The problem was that real galaxies didn't follow the Hubble flow exactly. When astronomers measured individual galaxy velocities carefully and compared them to what pure Hubble expansion predicted, there were systematic leftovers. Galaxies were moving at speeds and in directions that pure expansion could not account for. These deviations had a name: peculiar velocities. And in small amounts, peculiar velocities were expected. Local gravity, the pull of a nearby galaxy cluster, the tug of a neighboring group, would naturally push galaxies slightly off the smooth expansion baseline. That was normal. That was understood. What was not understood was the scale of what astronomers were beginning to see. By the 1970s and into the 1980s, galaxy surveys were growing large enough that a troubling pattern was becoming visible. Galaxies across an enormous volume of space, far larger than any individual cluster, far larger even than the Virgo Supercluster, seemed to be drifting coherently in roughly the same direction. Not just a handful of galaxies, not just one cluster. Thousands of galaxies spread across hundreds of millions of light-years were showing a systematic motion that pointed toward a particular region of the sky, somewhere in the direction of the constellations Centaurus and Norma. The motion was subtle, but it was measurable, and it was consistent. Something was pulling on a scale the existing maps would not explain. The Virgo Supercluster alone could not account for it. The gravitational influence of the Virgo cluster and its surrounding structure was well understood, and yes, it tugged on the local group. But this new signal was different, larger, deeper, coming from a direction and on a scale that pointed to something much more massive sitting further out, something that had never been properly identified or mapped. The clean hierarchy began to look incomplete. The top rung of the ladder seemed to be missing something, or rather, it seemed to be sitting on top of something larger that nobody had noticed. For a generation of astronomers, this was the uncomfortable feeling at the edge of the known map. The Virgo Supercluster was real. The hierarchy was real. But the hierarchy wasn't the whole story. The galaxies weren't just expanding outward uniformly. They were being pulled, subtly but unmistakably, towards something nobody had fully mapped. In the 1970s, when astronomers first produced detailed maps of the cosmic microwave background radiation, something immediately looked wrong. The CMB is the oldest light in the universe, a faint glow left over from roughly 380,000 years after the Big Bang, spread almost perfectly uniformly across the sky. Almost. When scientists looked carefully at their new maps, they noticed that one side of the sky was slightly warmer than the other. Not dramatically, not in a way that leapt off the page, but the asymmetry was real, and it was consistent, and it meant something specific. The Milky Way was moving, not just spinning in place, not just orbiting the center of our galaxy. The entire local group was being carried in a direction at a speed of roughly 600 kilometers per second toward a region of the sky nobody had properly investigated. 600 kilometers per second is not a small number. That is fast enough to cross the continental United States in under 10 seconds. At that speed, something is doing the pulling. The simple model of cosmic expansion, galaxies moving apart uniformly in all directions, like raisins in a rising loaf of bread, predicted no such drift. Everything should be moving outward from everything else. No preferred direction, no net flow toward any particular point. What the CMB maps were showing was a deviation from that picture. The local group had what astronomers call a peculiar velocity, meaning a velocity that cannot be accounted for by the ordinary expansion of space alone. Something gravitational was adding an extra tug. Peculiar velocities are the fingerprints of structure. In a perfectly smooth universe, galaxies would have no peculiar velocities at all. They would simply ride the expansion of space outward, evenly, in all directions. But the universe is not smooth. Matter is clumped into galaxies, clusters, filaments. Wherever mass concentrates, it pulls neighboring objects toward it, giving those objects a velocity component that points toward the mass rather than simply away from everything else. Measure enough peculiar velocities across a large enough volume of space, and you can reconstruct where the hidden mass is sitting. The CMB dipole was the first crude map of a peculiar velocity on the largest scale anyone had yet considered. It was telling astronomers that a significant mass concentration xi stead somewhere in the direction the local group was streaming toward, and that this concentration was large enough to accelerate thousands of galaxies simultaneously. Through the late 1970s and into the 1980s, several independent teams began measuring peculiar velocities for galaxies beyond the local group. What they found was alarming in its consistency. Galaxies in our general neighborhood were not just drifting outward with the Hubble flow, they were streaming. Hundreds of galaxies, spread across enormous distances, were all showing a common component of motion, pointed in roughly the same direction. This was not noise. This was a coherent bulk flow, a river of galaxies being carried together towards something. Astronomers called this the Great Attractor, and the name was chosen carefully. Whatever was out there was not a single object. It was a region, a concentration of matter so vast and so massive that its gravity was reaching hundreds of millions of light years in every direction and bending the trajectories of everything it touched. The 1986 paper that gave the Great Attractor its name came from a group of 7 astronomers who would become known informally as the 7 Samurai. Donald Lyndon Bell, Sandra Faber, and 5 colleagues had spent years building a catalogue of elliptical galaxies with measured distances and velocities. When they analysed the streaming motions in their data, they found that the bulk flow pointed toward a specific region of the sky, the direction of the constellations Norma and Centaurus Crux, roughly in the southern sky. Their best estimate placed the source of the gravitational pull at somewhere between 150 and 250 million light-years away. The mass required to produce the observed streaming was staggering. 10 million billion solar masses. That is a 10 followed by 15 zeros. That is n quadrillion suns concentrated into one region of space, exerting gravitational influence across a volume that makes our entire local group look like a single grain of sand on a beach. Stop and hold that number for a moment. 10 million billion solar masses. Our Sun is already so large that 1,000,000 Earths would fit inside it. The Milky Way contains somewhere around 200 to 400 billion stars. The entire mass of everything in the local group, every star, every galaxy, all the dark matter, all the gas, is perhaps a few trillion solar masses. The Great Attractor was something altogether different. It was not a cluster of galaxies in the ordinary sense. It was a concentration of mass that dwarfed entire superclusters, pulling the Milky Way and everything around it toward it at hundreds of kilometers per second, and it had apparently been doing this for billions of years. And yet, for most of the 1980s, nobody could see it properly. This is where the story gets genuinely strange. The Great Attractor was not a subtle signal buried in noisy data. Its gravitational effect was measurable across hundreds of millions of light years. Thousands of galaxies were streaming toward it. The CMB dipole was pointing at it. And yet when astronomers turned their telescopes toward the region of Norma and Centaurus and tried to actually observe this gravitational engine directly, they ran into a wall. Not a metaphorical wall. Something physical, sitting between us and the attractor, blocking the view. The Milky Way itself. Our galaxy is a disk. We are embedded inside that disk, roughly 2/3 of the way out from the center. When we look outward in the plane of the disk, toward what we see as the band of the Milky Way stretching across the night sky, we are looking through the maximum concentration of our own galaxy's stars, gas, and dust. There are hundreds of billions of stars between us and the edge of the galactic disk in that direction, along with enormous clouds of molecular gas and thick lanes of interstellar dust that absorb and scatter visible light almost completely. Anything sitting behind that disk, in visible wavelengths, is essentially invisible. Astronomers have a name for this region of the sky. They call it the Zone of Avoidance. The Zone of Avoidance covers a significant band across the entire sky. It is not a narrow slit. In some directions it extends 20 to 30 degrees above and below the galactic plane. A substantial fraction of the entire sky, perhaps 20% or more of the observable universe as seen from Earth, is obscured or seriously compromised in optical wavelengths by our own galaxy's disk. This would be merely inconvenient if the objects behind it were distributed randomly, but they are not. The Great Attractor sits squarely in this zone. The densest, most consequential structure in our corner of the universe happens to lie almost perfectly behind the thickest part of the galactic plane, as seen from our position within the Milky Way. You could not design a more effective obstacle if you tried. Astronomers throughout the 1980s and into the 1990s pushed hard against this limitation. They turned to radio telescopes, which can detect the 21-centimeter emission line of neutral hydrogen through almost any amount of dust. They used X-ray observatories, which can detect the hot gas in galaxy clusters, even through substantial obscuration. They developed infrared surveys that could cut through dust far more effectively than optical light. Slowly, painfully, the picture behind the Zone of Avoidance began to clarify. The Norma cluster emerged from the murk, a rich cluster of galaxies sitting right at the heart of the attractor region, dense with thousands of galaxies, threaded through with hot gas. It was not the totality of the Great Attractor, but it was a confirmation that something massive was genuinely there. The gravitational signal was real. The streaming was real. The thing causing it was real. What was almost absurd about the situation was the irony embedded in it. Here was the most gravitationally dominant structure within hundreds of millions of light-years of the Milky Way, something pulling our entire galactic neighborhood toward it at enormous speed, something that had been shaping the large-scale motion of galaxies in our region for billions of years. And the reason we could barely study it was not a technological limitation or a fundamental physical barrier. It was us. The very galaxy we live in was blocking our view of the gravitational engine at the center of our cosmic home. Imagine trying to map a city while standing in the middle of a thick forest that circles the entire downtown core. You can see what is directly around you. You can see patches of sky above. But the buildings at the center, the streets, the whole layout of the place you are trying to understand, all of it is blocked by the trees. That is roughly the situation astronomers face when they try to observe the region of the universe sitting behind the plane of the Milky Way. The forest is our own galaxy, and it does not move. The problem has a name. Astronomers call it the Zone of Avoidance, which sounds like something you would find on a nautical chart, warning ships away from shallow water. The name fits. It is a band running all the way around the sky, tracing the galactic plane, where the Milky Way's own stars, gas, and dust absorb and scatter the light coming from anything beyond. In optical wavelengths, the kind of light human eyes can see, this band is essentially opaque. Galaxies that sit behind it are not dimmed, they are gone. Their light never makes it through. The Zone of Avoidance covers roughly 20% of the entire sky. That is not a narrow strip you can work around. That is a fifth of everything, running in a continuous band around the full equator of our celestial sphere. What makes this strange is that the obscuring material is not particularly thick by cosmic standards. The dust and gas clouds responsible for the blockage are relatively diffuse, but they are spread across tens of thousands of light-years of galactic disk, and when you stack that much material between yourself and a distant galaxy, even thin stuff adds up. The total extinction in some parts of the galactic plane is enormous. Light from distant objects gets absorbed, scattered, and reddened into invisibility long before it reaches a telescope on Earth. Astronomers are not helpless. They found workarounds, and the workarounds are clever. Infrared light has longer wavelengths than visible light, and longer wavelengths cut through dust far more effectively. An infrared telescope can detect galaxies behind the galactic plane that are completely invisible to an optical instrument. X-ray observations help as well. High-energy X-rays punch through interstellar dust with relatively little scattering, which is how some of the galaxy clusters lurking behind the Zone of Avoidance were first identified. Radio wavelengths work too. The 21-centimeter emission line from neutral hydrogen passes straight through the galactic dust without any significant absorption, which means radio surveys can map hydrogen in distant galaxies, even when those galaxies are sitting directly behind the Milky Way's thickest regions. These tools opened up parts of the Zone of Avoidance that had been completely dark before. The Norma cluster, one of the major structures near the Great Attractor, was partly mapped through these techniques. Several previously unknown galaxy clusters were found hiding in the obscured region during the 1990s and 2000s, when systematic infrared and radio surveys swept across the galactic plane for the first time. Each discovery reminded astronomers how much had been missed simply because of where they happened to be sitting. But here is the thing. Even with infrared, X-ray, and radio data combined, The zone of avoidance remains the worst characterized region of the nearby universe. The tools that cut through dust come with their own limitations. Infrared surveys still struggle with the bright emission from our own galaxy's stars, which floods the detectors and makes faint background sources hard to extract. Radio surveys measure hydrogen, but miss galaxies with little neutral gas. X-ray observations pick up hot cluster gas, but not the full picture of galaxy distribution. No single alternative method gives you what optical astronomy gives you everywhere else. The coverage is patchier. The catalogues are less complete. The distance measurements are harder to make and less reliable. When Brent Tully's team built the Cosmic Flows 2 catalogue, the one that would eventually define Laniakea, the data thinned out and degraded precisely in the directions behind the galactic plane. The map had a hole in it, and the hole sat right over one of the most gravitationally significant regions in the local universe. There is a particular irony in all of this that is hard to ignore. The Milky Way is not a distant obstacle. It is not some intervening object that happens to lie in an unfortunate direction. It is the galaxy we live inside. The stars blocking our view of the Great Attractor are the same stars that make up the bright band of the Milky Way that humans have looked up at for all of recorded history. The dust blocking the light from thousands of background galaxies is the same dust that fills the spiral arms of our own home. We are embedded so deeply inside this structure that it wraps completely around us, and because of that, there is a ring around our entire sky where the universe is functionally hidden. The very thing that makes us astronomers, having a galaxy to stand in, is the same thing that blinds us to a fifth of what surrounds us. For years, the Great Attractor sat squarely behind this veil, its true nature hidden behind the very structure that contains every star you can see on a clear night. The breakthrough that produced Laniakea was not a new telescope or a new piece of hardware. It was a new idea about what astronomers should be measuring. For most of the 20th century, when astronomers tried to map the large-scale structure of the universe, they did it by counting. They would survey a region of sky, catalogue the galaxies they found, and draw boundaries around the densest concentrations. Where galaxies clumped together, that was a cluster. Where clusters grouped together, that was a supercluster. It was a logical approach. It was also, it turned out, incomplete. Density maps can tell you where matter piled up, but they cannot tell you what belongs together gravitationally. A city map that only shows population density misses the fact that commuters from far-flung suburbs are functionally part of the same metropolitan system, even if they live in a sparse neighborhood at the edge. Brent Tully understood this problem. Tully is an astronomer at the University of Hawaii's Institute for Astronomy, and by 2014, he had spent decades building the most precise catalogues of galaxy distances and velocities that the field had ever produced. He had already made his name decades earlier, co-developing the Tully-Fisher relation, the technique that links a spiral galaxy's rotation speed to its true brightness and allows astronomers to infer distances from observations alone. That earlier work was groundbreaking. But by the 2000s, Tully was working on something with even larger implications. He was thinking about what the motions of galaxies could reveal, not just their positions. Here is the key concept. When astronomers measure the velocity of a distant galaxy, they typically get two signals mixed together. One is the velocity from the expansion of the universe, the background hum of space itself stretching, which makes every galaxy appear to be moving away from us, faster with distance. The second signal is something subtler. It is the galaxy's individual motion on top of that expansion, caused by the gravitational tug of everything around it. Astronomers call this the peculiar velocity. It is the deviation from pure expansion, and it is a direct fingerprint of the local gravitational field. If you could map the peculiar velocities of thousands of galaxies across hundreds of millions of light years, you would not be looking at where galaxies happen to be sitting right now. You would be looking at where gravity is pulling them. You would see the underlying skeleton of the mass distribution, not just its surface appearance. This is what Tully and his collaborators set out to do. The analogy that makes this clearest is a watershed. Stand somewhere in the Rocky Mountains, and the rain that falls on your left flows eventually toward the Pacific. The rain that falls on your right flows toward the Atlantic or the Gulf of Mexico. There is a dividing line running along the mountain ridges where these drainage basins meet. On either side of that line, water flows in fundamentally different directions. Neither side knows anything about the other. They belong to different systems. Now imagine the same thing at cosmic scale. Galaxies are not sitting still. They are flowing, very slowly by human standards, toward the nearest major gravitational concentration. In one region, they flow toward one center of mass. In an adjacent region, they flow toward a different one. The boundary between those two regions, the cosmic equivalent of the continental divide, is where the peculiar velocities reverse direction. That boundary defines where one supercluster ends and another begins. Not a density threshold, a watershed. This was the conceptual breakthrough. A supercluster, under Tully's definition, is not simply a region where galaxies are dense. It is a basin of attraction, a volume of space inside which all galaxy motions, once you subtract the background expansion, are directed inward toward the same gravitational center. The boundaries are determined not by how many galaxies you can count per cubic megaparsec, but by where the flow changes direction. The method required data, enormous amounts of it. To construct a meaningful map of peculiar velocities across hundreds of millions of light years, you need precise independent distances for thousands of galaxies. Redshift alone does not work, because redshift conflates the expansion velocity with the peculiar velocity. You cannot separate them without an independent distance measurement. Tully and his colleagues had been building toward this for years. The result was the Cosmic Flows 2 catalog, containing measured distances for more than 8,100 galaxies spread across a substantial volume of the nearby universe. Each distance was derived using one or more of the established techniques, primarily the Tully-Fisher relation for spirals, along with other methods for other galaxy types. The kata log represented the most complete and precise dataset of its kind ever assembled. With those distances, the team could calculate each galaxy's peculiar velocity directly, subtract the expected expansion velocity, and what remains is real motion, gravitational flow. When you plot those flow vectors across thousands of galaxies, patterns emerge. Filaments of flow converging toward the same point, boundaries where flow directions diverge. The invisible architecture of gravity made visible through the motion of light. The computation was not trivial. Converting raw distance and velocity measurements for thousands of galaxies into a coherent three-dimensional flow map required sophisticated mathematical reconstruction. The team had to account for gaps in coverage, errors in individual distance measurements, and the contaminating effects of the Zone of Avoidance, where peculiar velocity data was thin or absent. They developed techniques to smooth and reconstruct the flow field across poorly sampled regions, using the surrounding data to fill in the gaps as accurately as possible. It was as much mathematical craft as astronomical observation. When the paper landed in Nature on September 4, 2014, it presented not just a new structure, but a new framework. Every previous map of the local supercluster had drawn its borders based on galaxy density. Tully's map drew borders based on gravitational coherence. The result was a structure vastly larger than anyone had previously outlined, one that absorbed the old Virgo Supercluster as a single component, that stretched 520 million light-years from one side to the other, and that contained roughly 100,000 large galaxies, all flowing, however slowly, toward a common gravitational center. The Great Attractor, which had mystified astronomers for decades, turned out to be the heart of this basin. It was not a strange anomaly in an otherwise simple universe. It was the gravitational flaw of the largest structure any of us had ever lived inside. What made the work genuinely significant was not the size of what it found, though the size was staggering. It was the redefinition of the thing being measured. Tully's team did not discover that the universe was bigger than we thought. They changed the question. Instead of asking where the galaxies are, they asked where the galaxies are going. That shift in question produced a shift in structure, a new way of drawing the map of our cosmic address that nobody had managed before. When they applied it to over 8,000 galaxies with measured distances and velocities, the shape that emerged from the data was enormous, coherent, and unlike anything on the existing maps. The structure that emerged from Tully's maps was 520 million light-years across. That number is easy to type and almost impossible to hold in your mind. But let's try. The Milky Way, our galaxy, the one containing our Sun and every star visible on a clear night, stretches roughly 100,000 light-years from one edge to the other. That already sounds enormous. Light, traveling at 186,000 miles per second, takes 100,000 years just to cross it. Yet if you wanted to line up Milky Way-sized galaxies end to end and span the full width of Laniakea, you would need 5,000 of them. Not 5, not 50. 5,000 galaxies, each containing hundreds of billions of stars, laid side by side, and you still haven't reached the other end. That is what 520 million light-years means in practical terms. It is a number that defeats ordinary intuition entirely. The mass locked up inside this structure is just as staggering. Laniakea contains roughly 100,000 large galaxies. Each of those galaxies is, by any human measure, incomprehensibly large. But the total mass of Laniakea isn't just the mass of the stars inside those galaxies. It includes the dark matter halos wrapped around each one, the hot gas filling the space between galaxies, and the gravitational glue holding clusters together. Add it all up, and you get something in the range of 10 to the power of 17 solar masses. That's a 1 followed by 17 zeros, measured in suns. 100 quadrillion suns. Written out as a number, it has so many digits that the number itself becomes meaningless to read. The human brain simply doesn't have a reference frame for it. There is no analogy that fully survives contact with this scale. What does Laniakea actually look like? This is where it gets genuinely strange. It is not a sphere. It is not a uniform cloud. It does not have smooth edges or a clean center. If you could somehow generate an image of it in 3 dimensions and step back far enough to see the whole thing at once, what you would see looks something like a crumpled, sprawling web. Dense, bright knots mark where massive galaxy clusters sit. Thin threads connect them, filaments made of galaxies and gas, stretching for hundreds of millions of light years between the nodes. And between those filaments, there is almost nothing. Vast regions of dark, empty space where galaxies are rare or absent entirely. The structure has shape and anatomy, but nothing about that shape is neat or symmetrical. Think of it less like a ball and more like a handful of soap bubbles smashed together and stretched. The walls of the bubbles are the filaments, the places where galaxies concentrate. The air inside each bubble is a void. Where multiple bubbles meet, the concentration of matter is highest. Those are the clusters. Laniakea is the region defined by one connected system of these filaments and flows, all of it draining gravitationally toward a common center. That center is what astronomers call the Great Attractor, a region deep inside Laniakea where the gravitational pull is strongest. Galaxies across the full 520 million light-year span of the structure are moving slowly in that direction, not because they are being pushed, but because gravity has been pulling on them for billions of years and they have built up a drift. This motion is subtle. You would not notice it over a human lifetime, but measured in kilometers per second, the infall toward the Great Attractor is real and detectable. It is what allowed Tully's team to define the structure in the first place. The watershed flows all run toward this gravitational basin. That's where the center of Laniakea is. Now here is the part that changes how you think about where you are. The Milky Way does not sit anywhere near that center. It sits on the edge, the outskirts, the rim. Depending on how you measure it, our local group is somewhere around 150 to 250 million light years from the Great Attractor. That means we are not in the middle of Laniakea. We are roughly halfway to the edge, on the outer fringe, in a relatively sparse and quiet part of the structure. There are no major galaxy clusters nearby. There is no dramatic concentration of matter in our immediate vicinity. We are in the low-density outer region of an enormous gravitational basin, and the heart of that basin is hundreds of millions of light-years away. This should be a genuinely disorienting realization. For most of human history, humans assumed they occupied a special or central place in the cosmos. Copernicus moved the Earth away from the center of the solar system. Later work moved the Sun away from the center of the galaxy. Now, Laniakea moves us away from the center of our own supercluster. Whatever the center of things might be, we are not near it. We are peripheral in every structure we have ever managed to identify. There is something worth sitting with there. The Great Attractor is pulling us toward it. Our local group is drifting, incredibly slowly, in that direction. But we are not falling fast. The distance is so enormous and the drift so gradual that it will take billions of years to cover even a fraction of it. And dark energy, the force accelerating the expansion of the universe, will likely pull the outer regions of Laniakea apart before any dramatic convergence happens. We are moving toward the center of our supercluster, but the supercluster itself is dissolving as we go. It is not a destination we will ever reach. The overall architecture of Laniakea, when you map it out with the flows and the clusters and the filaments, divides into several major regions. There is the part containing the Virgo cluster and our local group, the part containing the Hydra and Centaurus clusters, the region around the Norma cluster near the Great Attractor itself, and the Parvo-Indus Supercluster region further out. These are not cleanly separated neighborhoods. They are connected by filaments, blending into each other the way the suburbs of a city blend into its outskirts. But the rough anatomy is there, and it all connects into a single, coherent gravitational basin. One thing that the three-dimensional maps make very clear is how much empty space there is. The filaments are thin. The clusters are relatively compact. Most of the volume of Laniakea is void. If you were a traveler moving through this structure at random, you would spend the vast majority of your journey in near-empty darkness, far from any galaxy. The bright connected web that shows up on the maps represents a tiny fraction of the total volume. Most of Laniakea is nothing, and yet, even knowing all that, 100,000 large galaxies is not a small number. Spread across 520 million light-years, they fill this structure with an almost uncountable number of stars, planets, and everything else. The Milky Way alone has somewhere between 100 and 400 billion stars. Multiply that by 100,000 galaxies, and even a rough estimate becomes a number that no human can meaningfully visualize. Whatever is out there in Laniakea, whatever is in those galaxies, on those planets, around those stars, it exists at a scale that makes the entire history of human civilization look like a footnote written in pencil on the last page of a book inside a library that fills a continent. The structure is real. It is not a theoretical construct or a statistical artifact. It is a physical feature of the universe we live in, defined by the actual motions of actual galaxies across actual space. And the Milky Way, with all its hundreds of billions of stars, sits near the outer edge of this, a small dot on the rim of something almost too large to picture. When the time came to name the structure, Brent Tully did not reach for Greek or Latin. Most astronomical discoveries get named after their discoverers, or after constellations, or after the catalogues they appeared in. Tully's team was working at the University of Hawaii. They were embedded in a place with its own deep language, its own history of navigating enormous and featureless expanses, and its own tradition of reading the sky. So Tully did something unusual. He consulted with Hawaiian language experts to find a name that fit what they had actually found. The word they landed on was Laniakea. It comes from two Hawaiian roots. Lani means heaven, or sky, or the celestial realm above. Akea means spacious, open, immeasurable. Together the phrase means something like immense heaven, or the expansive sky, a realm of stars so vast it resists ordinary description. The name was suggested by Nawaa Napoleon, an associate professor of Hawaiian language at Kapiolani Community College. It was not a casual choice. It captured something real about the scale of the thing being named, a structure 520 million light-years across, containing 100,000 galaxies, bigger than anything our nearest ancestors could have conceived. Immense heaven is not an exaggeration. It is barely adequate, but there is something stranger and more interesting here than just a well-chosen word. The name carries a cultural weight that runs directly parallel to the science behind it. Polynesian navigators crossed the Pacific Ocean, the largest body of water on Earth, without compasses, without GPS, without charts in the modern sense. They crossed it by reading the sky. They memorized the rising and setting points of hundreds of stars. They understood how ocean swells move relative to wind and island chains. They track the color of the water, the flight paths of birds, the feeling of current against a hull. But above all, they read the heavens. The sky was their map. The sky told them where they were. These were not short journeys. The Pacific spans more than 12,000 miles at its widest. Ancient Polynesian navigators reached Hawaii, New Zealand, Easter Island, and dozens of other island groups separated by thousands of miles of open ocean, with no landmarks visible from the water. They did it by knowing the sky better than any civilization in history. The sky was not decoration to them. It was orientation. It told you which way was home. Now consider what Tully's team actually did. They spent years mapping how 8,000 galaxies move through space. They tracked the flows, the convergences, the divergences, the subtle gravitational currents running beneath the smooth expansion of the universe. And by reading those flows, they found our address. Not our street address, not our galaxy, our supercluster. They used the motion of the cosmos to figure out where we are inside it. They navigated by reading the sky. The parallel is not decorative, it is exact. The navigators who crossed the Pacific were doing something that looks, from the outside, like it should be impossible. How do you find a small island in an ocean that wide, using only the sky? The answer is that you know the sky well enough that it becomes a coordinate system, a live map of your position and heading. Tully's team was doing something that also looks, from the outside, like it should be impossible. How do you find the shape of a structure 520 million light-years across when you are inside it and can only observe from a single point? The answer is that you read the flows well enough that they reveal the shape of the basin you are sitting in. There is something almost too fitting about this. The name Laniakea honors a tradition of navigation that solved the same fundamental problem at a completely different scale. Where are we? Which way is home? How do you find your position in a featureless expanse with no obvious landmarks? The Polynesian answer was the stars. Tully's answer was the motion of galaxies. Both are forms of reading the sky to find your place within it. Noir Napoleon's suggestion was not just linguistically appropriate, it was philosophically accurate. The sky to Polynesian navigators was not a background, it was a location system. And that is precisely what Laniakea is. A location, a place in the cosmos that has a structure, a shape, a center, a set of flows defining its edges. For the first time in history, we have a name for the largest structure we belong to, and that name comes from a people whose entire civilization was built around the idea that the sky tells you where you are. That is a strange kind of symmetry. The navigators who crossed the Pacific by reading the heavens had no way of knowing what those heavens were embedded in. They knew the stars as guides. They did not know those stars were part of a galaxy, or that the galaxy was part of a supercluster, or that the supercluster had a name. Now it does. The people who learned to cross the Pacific by reading the sky gave their language to the discovery of where that sky actually sits in the universe. The Virgo Supercluster did not disappear when Laniakea was defined. It simply shrank in significance. For decades, the Virgo Supercluster was the best answer astronomers had to the question of our large-scale cosmic home. It was a genuine structure. It was real. Roughly 100 million light-years across, centered on a dense knot of galaxies in the direction of the constellation Virgo, It had been identified in the 1950s by astronomer Gérard de Vaucouleurs and refined by generations of researchers who followed him. If you had asked a cosmologist in 1990 where the Milky Way lived in the largest known structure, the answer was the Virgo Supercluster, and that answer felt solid. It felt complete. It had been tested and mapped and written into textbooks. When Laniakea arrived in 2014, it did not invalidate any of that work. It just revealed that the work had been describing a neighborhood without realizing the city extended far beyond it. The Virgo cluster itself sits near the heart of this older structure, and it is worth pausing on what that cluster actually is. Several thousand galaxies packed into a region roughly 15 million light-years across. Not a loose scattering, but a genuine gravitational city, one of the richest concentrations of galaxies within several 100 million light-years of Earth. It anchors the Virgo Supercluster the way a downtown core anchors a metropolitan region. Its mass pulls on everything around it. The local group, the small collection of roughly 80 galaxies that includes the Milky Way and Andromeda, is moving toward the Virgo cluster right now, very slowly, tugged by its gravity across 50 to 60 million light-years of intervening space. The Virgo cluster is not abstract. It is a real gravitati, onal presence, something our entire galactic neighborhood feels. But the local group's position in all of this is worth examining closely. Roughly 80 galaxies, most of them small satellites orbiting either the Milky Way or Andromeda. The two dominant members, our galaxy and its large neighbor, are themselves unremarkable spiral galaxies by the standards of the broader universe. The local group sits in the outer regions of the Virgo Supercluster, not near its center. Then the Virgo Supercluster itself, as Laniakea revealed, occupies an outer region of Laniakea. Stack these positions together and a clear picture forms. We are not near the center of our galaxy cluster. Our cluster is not near the center of the Virgo Supercluster. The Virgo Supercluster is not near the center of Laniakea. At every level of the hierarchy, we are somewhere on the periphery, a pattern that seems almost deliberate, but is simply what the data shows. The conceptual demotion this represents is worth sitting with. Every level of our cosmic address that had felt like a meaningful designation, Virgo Supercluster, home, the largest structure we belong to, turned out to be a subdivision of something larger. It is like being told that the city you have lived in your whole life, the city whose name you gave when people asked where you were from, is not a city at all. It is a district, and the actual city is 5 times bigger, extends in directions you were not looking, and contains structures in its other districts you have never seen. The name on your driver's license did not change. You did not move, but your sense of where you are shifted completely. This kind of conceptual reshuffling has happened before in astronomy. Earth was not the center of the solar system. The Sun was not the center of the galaxy. The Milky Way was not the only galaxy. Each revision followed the same pattern. A structure that seemed like the largest relevant frame turned out to be a component of something larger. The Virgo Supercluster joining this list was not a shock to anyone paying attention to the history of the field, but it was still a genuine revision of the scientific record. Every textbook that had listed the Virgo Supercluster as our supercluster needed an asterisk, if not a rewrite. What Laniakea absorbed was not just a name on a map. The Virgo Supercluster had been associated with a specific picture of cosmic structure, a set of boundaries, a hierarchy. That picture was not wrong, exactly. The galaxies are still where they were. The flows are real. The Virgo cluster still dominates its local region of space. But the boundaries that defined the Virgo supercluster as an independent entity were revealed to be permeable, artificial in a certain sense, drawn around a density peak rather than around a true gravitational basin. When Tully's team redrew those boundaries using flow patterns instead of density, the Virgo supercluster was absorbed. It became one region in a much larger structure, like a borough absorbed into a growing metropolis that had expanded far beyond its original limits. There is something almost vertiginous about this if you follow it all the way down. The Milky Way is one of roughly 80 galaxies in the local group. The local group is one of perhaps 1,000 groups and clusters in the Virgo supercluster. The Virgo supercluster is one of several major components within Laniakea. Laniakea contains something on the order of 100,000 large galaxies spread across 520 million light-years. At each step, the scale multiplies, and the previous frame of reference shrinks. Our galaxy, which contains hundreds of billions of stars, is a minor entry in a minor cluster on the outer edge of a supercluster component that is itself an outer region of the structure we actually live in. None of this diminishes what the Virgo supercluster is. It is still a real and massive structure. The gravitational influence of the Virgo cluster on our local group is real and measurable. But calling the Virgo supercluster our home supercluster, the way astronomers did for half a century, was like calling a suburb the city. What we had called home for half a century turned out to be one small corner of a much larger room. Laniakea is not a smooth, uniform cloud of galaxies. It has bones. If you could somehow pull back far enough to see the whole structure at once, the way you might look down at a city from altitude on a clear night, what you would see is not a featureless glow. You would see something more like a nervous system. Bright knots of light where clusters sit. Long, faint threads connecting them. And between those threads, enormous darkness, not empty by accident, but empty because gravity spent billions of years pulling matter away from those regions and piling it somewhere else. The voids are not gaps in the data. They are real features, as much a part of the structure as the clusters themselves. The major galaxy clusters inside Laniakea read like a catalogue of the southern and equatorial sky. Virgo is the closest significant one to us. Hydra and Centaurus sit deeper in, part of a dense complex that blends into the gravitational center of the whole structure. The Norma cluster lies close to the Great Attractor itself, embedded in the most crowded region of Laniakea's interior. Ophiuchus is one of the most massive clusters in the entire supercluster, holding an enormous concentration of hot gas and hundreds of galaxies bound tightly together. Fornax and Eridanus anchor a separate region of the structure, part of the southern extension of the filamentary web. These are not just names on a list. Each one represents a gravitational knot that has been accumulating matter for most of the age of the universe. A galaxy cluster forms because the universe was never perfectly smooth. In the earliest moments after the Big Bang, there were tiny variations in density. Some regions had slightly more matter, some slightly less. Those differences were almost imperceptibly small. But gravity is patient. Over hundreds of millions of years, the slightly denser regions pulled more matter toward themselves. That made them denser still. Other matter fell in from surrounding areas. Eventually, those regions collapsed into the first galaxies. Galaxies fell toward each other, grouping into clusters, and clusters gathered into superclusters. What you see in Laniakea now is the result of that process running for roughly 13 billion years. The clusters are where gravity won most decisively. The voids are where it was too thinly spread to win at all. The assembly process did not stop once the initial clusters formed. Smaller clusters and galaxy groups continued falling into larger ones throughout cosmic history, their mergers releasing tremendous energy. A massive cluster like Virgo or Centaurus did not reach its present configuration until relatively recently, on cosmic timescales. Clusters continue to grow and evolve, incorporating isolated galaxies that venture too close to their gravitational influence. The largest clusters have been accumulating matter steadily for billions of years, and some are still in the process of merging with neighboring structures today. This ongoing accretion gradually reshapes the cluster environment and increases total mass. The clusters visible in Laniakea are not static monuments to ancient gravity, but dynamic systems still assembling and growing, drawing matter inward through the cosmic web. Inside a cluster like Virgo or Norma, individual galaxies are not sitting still. They move at speeds of hundreds or even thousands of kilometers per second, orbiting the cluster's center of mass the way bees circle a hive. The space between them is filled with extremely hot, diffuse gas, so hot it emits X-rays, and all of it is held together by the combined gravity of the galaxies, the gas, the dark matter that makes up the majority of the cluster's total mass. A rich cluster can contain anywhere from hundreds to several thousand galaxies. The Virgo cluster alone holds several thousand. That kind of density is genuinely strange when you think about what galaxies are. Each one of those is a structure containing hundreds of billions of stars. They are packed together tightly enough to interact, distort each other, and occasionally merge. The filaments that connect these clusters are harder to see, but just as real. They are elongated structures, rivers of galaxies flowing between the dense nodes of the web. A single filament inside Laniakea might stretch for 100 million light-years or more, containing thousands of galaxies arranged loosely along its length. These are not solid structures. There is enormous space between the galaxies inside a filament, but statistically, the galaxy density along a filament is meaningfully higher than in the surrounding voids. Gravity draws matter toward the filaments, and the filaments drain toward the clusters at their ends. The whole thing flows, slowly, toward the densest concentrations. Then there are the voids. Cosmological voids are among the strangest objects in the universe, if you can call an absence an object. They range in diameter from about 30 million light-years on the small end to 300 million light-years for the largest known examples. Inside a void, the mean density of matter is less than 1/10 of the cosmic average. Galaxies are not absent entirely. There are isolated galaxies and small groups scattered through void regions, but they are so sparse that the void is, on cosmic terms, essentially empty. If you lived in a galaxy inside one of the large voids bordering Laniakea, your view of the night sky would be far lonelier than ours. The nearest large galaxy cluster might be 100 million light-years away. The universe would look far emptier than it do, as from our position. What makes this architecture striking is that it is not unique to Laniakea. The same pattern, clusters at the nodes, filaments connecting them, voids filling the space between, appears everywhere in the observable universe at these scales. Cosmologists call it the cosmic web. It is the large-scale structure of the universe, and it was not designed. It emerged naturally from gravity, acting on the tiny density fluctuations left over from the earliest moments of cosmic history. Simulations that start from the conditions of the early universe and run the physics forward reproduce this filamentary structure automatically. The web was always going to form this way, given those initial conditions. Laniakea is one node in that larger web, surrounded by neighboring superclusters that have the same internal architecture of clusters, filaments, voids, each one connected to others across distances that dwarf even Laniakea itself. This matters for how you think about what Laniakea is. It is not a bounded object floating in empty space. It is a region of the cosmic web that has a coherent gravitational basin, a region where galaxy motions converge toward a common center, but its edges blend into surrounding structures that are themselves organized the same way. The filaments inside Laniakea connect outward to filaments in neighboring superclusters. The voids inside Laniakea open onto voids that extend far beyond its defined boundary. The structure has no sharp walls. It fades, bleeds outward, continues. From inside, living in a galaxy on the outer edge of one of the smaller filamentary extensions, you see almost none of this. You see a sky full of stars that all belong to your galaxy. You see a handful of nearby galaxies with a telescope. If you look at the distribution of distant galaxies across the whole sky with a powerful enough survey, you start to see hints of the filamentary structure, overdense regions in some directions, underdense regions in others. But the full three-dimensional picture, the bones of Laniakea, only becomes visible when you map thousands of galaxies across hundreds of millions of light years and trace how they are moving. This is not a structure you would recognize from the inside. That is exactly why it took until 2014 for anyone to draw its full outline. Here is the strange part. Laniakea is not actually held together. There is a difference between a gravitationally bound structure and a basin of attraction. A gravitationally bound structure is one where gravity wins, where the objects inside it are locked together tightly enough that expansion cannot pull them apart. Galaxy clusters are bound. The Virgo cluster, sitting near the center of our local corner of Laniakea, holds thousands of galaxies in a gravitational grip they will never escape. Those galaxies are not going anywhere. They will continue orbiting, colliding, eventually merging over tens of billions of years into something unrecognizable, but they will stay together. Our own local group is bound. The Milky Way and the Andromeda Galaxy are falling toward each other right now, closing the gap at roughly 110 kilometers per second. In about 4.5 billion years, they will collide. That is a gravitationally bound system behaving exactly as bound systems do. Laniakea is something different. Its galaxies are not locked to each other. They are simply flowing in the same direction, pulled toward the Great Attractor, the way water flows toward the lowest point in a valley. The structure has coherence because the flows are real and measurable. But coherence is not the same as a bond. A river has coherence. The water moves together in a shared direction, following the same gradient. But the river does not hold itself together. It flows because the landscape underneath it slopes a certain way. Remove the slope, and the river stops. Laniakea is similar. Its structure exists because the gravitational landscape of this region of space slopes inward toward the Great Attractor. The galaxies follow that slope. Right now, in this epoch of cosmic history, that slope is real enough to define an enormous, coherent supercluster, but there is something else shaping that landscape. Dark energy is real. It is the dominant energy component of the universe, and it is working against gravity at every scale large enough for the expansion of space to matter. On the scale of galaxy clusters, gravity wins. On the scale of superclusters, the contest is closer. On the scale of Laniakea, dark energy is already winning at the outer edges. The expansion of the universe is not uniform in its effects. Galaxies that are gravitationally bound to each other are immune. The expansion of space does not reach in and tear apart structures that are already gravitationally locked. But galaxies on the outer fringes of Laniakea, where the gravitational pull from the center is weaker and the distances are greater, are in a different situation. For those galaxies, the outward push of cosmic expansion is already comparable to, or greater than, the inward pull of gravity. Over time, that balance tips further toward expansion. The outer galaxies drift. Then they accelerate away. The boundary of the structure does not hold. Think about what this means practically. Right now, a galaxy near the edge of Laniakea is technically part of the supercluster. Its motion, if you subtract out the general expansion of the universe, points inward. It is part of the flow. But over hundreds of billions of years, the expansion rate increases relative to the gravitational attraction, and at some point, that galaxy's peculiar velocity, the inward drift that makes it part of Laniakea, gets overwhelmed by the expanding universe carrying it away. The galaxy tips over the Watershed divide and effectively leaves the supercluster. Not dramatically, not suddenly, just gradually, inexorably, as cosmic expansion stretches the space between it and the Great Attractor until gravity can no longer bridge the gap. This happens first at the edges and works inward. The filaments connecting distant clusters weaken and eventually dissolve. The clusters themselves remain intact. They are bound, but the threads linking them across hundreds of millions of light years slowly break. The supercluster's architecture, that web of bright nodes connected by strands of galaxies, gradually loses its connections. The nodes persist. The web does not. The Great Attractor does not switch off. It remains a massive concentration of matter, and it continues pulling nearby galaxies toward it. But its gravitational reach has a limit, and that limit gets shorter as dark energy drives space to expand faster. Currently, the Great Attractor's influence extends across the full scale of Laniakea, roughly 250 million light-years in all directions. Over hundreds of billions of years, the region where its gravity beats out expansion contracts. More and more of the supercluster's outer volume crosses over into territory where expansion wins. What you are left with, eventually, is not Laniakea. You are left with a collection of bound galaxy clusters, each isolated, each intact within itself, but separated from all the others by expanding voids too large for gravity to bridge. The Great Attractor's neighborhood survives as a dense core. The outlying regions drift away into the darkness. nothing remains to show that these clusters were ever connected, that galaxies across 520 million light-years once all flowed toward the same gravitational basin. This is the strange status Laniakea holds. It is real. The flows that define it are measurable. The structure that Brent Tully's team drew in 2014 is coherent and meaningful. And yet it is not permanent in the way that a galaxy is permanent, or a star, or a planet. It exists as a structure only because we happen to be living in an epoch when its coherence is intact, when the gravitational flows are strong enough relative to expansion to give it definable shape and definable borders. In a universe older than ours by a factor of 10 or 100, there would be no Laniakea to find. There would be no flow to map. We mapped it just in time, in a sense, a structure coherent enough to define today, but destined to dissolve over timescales longer than the current age of the universe. To define a structure by how galaxies move, you first have to know where those galaxies actually are. That sounds obvious. It is, in practice, one of the hardest problems in observational astronomy, and solving it took the better part of 5 decades. Here is the core difficulty. You cannot lay a measuring tape across space. You cannot bounce a signal off a galaxy 100 million light-years away and time the echo. Every method astronomers have for measuring cosmic distances is indirect. Each one rests on a physical relationship, something that connects a property you can observe to a property you cannot directly measure. And each one carries error. Small errors in distance, when converted into peculiar velocities, produce large errors in the flow maps. The flow maps are only as clean as the distances underneath them. Everything that makes Laniakea real and mappable and coherent traces back to this unglamorous problem of actually pinning down where things are. The way astronomers approach this is through what they call the distance ladder. The idea is to build outward in steps. Each step uses a method that works reliably over a certain range of distances, but fails beyond it. Each new method gets calibrated against the previous one before you trust it at greater distances. The bottom rungs of the ladder are close enough that geometry alone can do the work. Parallax, the tiny apparent shift in a nearby star's position as Earth orbits the Sun, works out to a few thousand light-years. Above that, you switch to a different technique. At each transition, you are trusting that the calibration between methods is solid, because any error there propagates upward through every measurement you make at greater distances. To reach galaxies hundreds of millions of light-years away, you need methods that work at truly enormous scales. Two of the most important are the Tully-Fisher relation and the fundamental plane, and together they are responsible for most of the data that went into defining Laniakea. The Tully-Fisher relation applies to spiral galaxies. It was noticed in 1977 by Brent Tully and J. Richard Fisher, and the same Tully would later lead the Laniakea team. What they found was a tight correlation between how fast a spiral galaxy rotates and how intrinsically luminous it is. A galaxy spinning faster is more massive, and more massive galaxies are brighter. If you measure a spiral galaxy's rotation speed, you can infer how bright it truly is. Then you compare that true brightness to how bright it appears in the sky. The difference tells you how far away the light must have traveled to look as faint as it does. It's the same logic as knowing how powerful a light bulb is and using its apparent dimness to estimate how far down the street it sits. The challenge is precision. Small uncertainties in the rotation speed measurement translate into distance errors. Calibrating the relation required extensive work across nearby galaxies where independent checks were possible. For elliptical galaxies, which don't rotate the same way, a different method applies. Elliptical galaxies follow what astronomers call the fundamental plane, a relationship involving three observable quantities: the galaxy's size, its surface brightness, and the velocity dispersion of its stars, basically how fast the stars are moving relative to each other internally. These three properties are not independent. They are linked by the underlying physics of how elliptical galaxies form and evolve. If you measure two of them, you can infer the third, and from the inferred properties you can extract the true luminosity, which again gives you distance. The fundamental plane is messier than Tully-Fisher in some respects, with more scatter in the relationship, but it extends the distance ladder to galaxy types that Tully-Fisher cannot reach. The Cosmic Flows project, led by Tully and his team, was built to gather these measurements in systematic, large numbers. The Cosmic Flows 2 catalogue, which fed directly into the 2014 Laniakea paper, contained distances for more than 8,100 galaxies. That number sounds large until you realize how vast the volume of space being mapped actually is. At the outer edges of the survey, the coverage was thin. Individual galaxies were separated by gaps where no measurements existed. The flow maps in those regions were smooth interpolations between real data points. Every boundary on the Laniakea map is only as sharp as the data density behind it allows. What Cosmic Flows 4, released years later, brought was scale. Nearly 56,000 galaxy distances, gathered using 8 separate methodologies cross-checked against each other. The expanded catalogue allowed the flow maps to extend further and resolve structure more finely. It also allowed genuine tests of whether the 2014 boundaries held up under scrutiny from a dataset 7 times larger. Mostly they did, which is itself a statement about how solid the original analysis was, despite the sparse coverage. It is worth being specific about how much human effort this represents. Measuring rotation curves for thousands of spiral galaxies requires deep spectroscopic observations, long nights at large telescopes, careful sky subtraction, and painstaking reduction of the raw data. It requires doing this for galaxies that appear as faint smudges in the sky. It requires going back and remeasuring, checking for systematic errors, updating calibrations as better nearby anchor points become available. The Cosmic Flows catalogues reflect observational campaigns stretching back to the 1970s, accumulated across hundreds of telescope nights at facilities from Hawaii to the Canary Islands to Chile. Nobody did this in a single coordinated push. It accumulated piece by piece, researcher by researcher, over 4 decades, until the database was large enough and reliable enough to trace the flows that outlined Laniakea. The map of Laniakea is only as reliable as the distances that went into building it, which means it rests on decades of unglamorous observational work that most people never hear about. If Laniakea had a neighborhood, the Shapley Supercluster would be its nearest significant neighbor, and the relationship between them is not simple. The Shapley Supercluster sits roughly 650 million light-years away. That is several hundred million light-years further out than the Great Attractor, which already sits 150 to 250 million light-years from the Milky Way. By any measure, Shapley is distant, but distant does not mean irrelevant. Shapley is one of the most massive concentrations of matter in the observable universe, and its gravitational influence reaches far beyond its own boundaries. When astronomers began measuring the peculiar velocities of galaxies throughout and around Laniakea, something strange kept showing up in the data. The Great Attractor was not just pulling nearby galaxies toward itself, it was also moving. The entire gravitational center of Laniakea was drifting, being pulled in Shapley's direction. This is where the picture gets complicated. Laniakea was defined as a basin of attraction, a region where galaxy motions converge inward toward a shared gravitational center. That definition worked cleanly within its mapped boundaries. But the Great Attractor at Laniakea's core is itself part of a larger flow. Something with even more mass is pulling on it from further out. The Shapley concentration, as astronomers sometimes call it, generates a gravitational pull strong enough to tug on a structure containing 100 quadrillion solar masses. Which raises a real question. Is Laniakea truly an independent basin, or is it a smaller valley inside a larger one that drains ultimately towards Shapley? There is no clean answer yet. Some analyses suggest Laniakea and the Ophiuchus cluster region form a combined basin that flows towards Shapley, which would make Laniakea a sub-basin rather than a top-level structure. Others maintain that the flow patterns are distinct enough to treat them separately. The boundary is fuzzy. That fuzziness is not a failure of science. It reflects the fact that the universe does not organize itself into tidy boxes. Gravity does not stop at the edges of whatever structure we choose to name. Then something else turned up entirely. In 2020, a team of astronomers announced the discovery of a massive structure lying just beyond Laniakea's boundaries. They called it the South Pole Wall. The name comes from its orientation in the sky, concentrated near the south celestial pole and extending outward in a great sweeping arc. The scale of it is hard to take in. The South Pole Wall stretches across roughly 200 degrees of sky, more than a semicircle. It wraps around Laniakea like an arm. The densest part of the structure sits about 500 million light-years from the Milky Way, but following the arc northward, it curves inward to within 300 million light-years of us. It is not some distant background feature. It is immediately adjacent. What makes the South Pole Wall particularly striking is how long it went unnoticed. Part of the answer is the Zone of Avoidance. A significant portion of this structure lies behind the galactic plane, hidden behind the dust and gas of the Milky Way. The tools that revealed it, the same peculiar velocity mapping technique used to define Laniakea, are better at seeing through that obstruction than optical surveys. The South Pole Wall is a reminder that Laniakea does not float in empty space. It sits within a rich, dense cosmic environment, bordered by enormous structures that we are still in the process of cataloguing. In 2023, a study using the Cosmic Flows 4 catalogue pushed this work further. Cosmic Flows 4 contains distances for nearly 56,000 galaxies, compared to the 8,100 used in the original 2014 Laniakea paper. With that much more data, the Watershed technique could be applied at larger scales and with better precision. The result was a map that confirmed Laniakea's size and shape, and simultaneously identified 5 neighboring superclusters using the same method. Those neighbors are Shapley, Perseus Pisces, Hercules, Lepus, and Apus. Each one is a distinct gravitational basin in its own right, a region where galaxy motions converge inward, just as they do within Laniakea. Each one is enormous, and each one sits adjacent to Laniakea in a way that makes the entire local region of the universe feel increasingly crowded and interconnected. Perseus Pisces is one of the largest concentrations of matter in the nearby universe, a long filamentary structure stretching across hundreds of millions of light years in a completely different direction from Shapley. Hercules sits further out, a less concentrated but still massive structure. Lepus and Apus are less studied, less well characterized, identified primarily through the flow signatures in the Cosmic Flows 4 data, rather than through dense optical surveys. These are not minor footnotes, they are superclusters, and Laniakea sits among them, not at the edge of organized structure, but deep inside a web of it. This brings in the Pisces-Cetus Supercluster complex. This is an even larger organizational level, a structure that contains Laniakea, Perseus Pisces, Cetus, and several other components in a single elongated complex stretching across roughly 1 billion light-years. The Pisces-Cetus complex is among the largest known structures in the observable universe. Laniakea is its inner component, its central region, which means the structure we spent so much effort defining, the one that took decades of observational work to map, is itself a neighborhood inside something far larger. There is a pattern here. Before 2014, our largest named home was the Virgo Supercluster. Then Laniakea absorbed it and grew the answer by a factor of 5 in diameter. Now, Laniakea sits inside the Pisces-Cetus complex and flows towards Shapley. Each time astronomers step back and look at a larger volume, the structure does not end. It continues. New walls, new clusters, new basins of attraction keep appearing at the edges of whatever map was just completed. This is not a coincidence. It is what the physics predicts. Gravity has been operating on matter for 13 billion years, pulling density enhancements into galaxy clusters, pulling clusters toward each other along filaments, pulling superclusters into still larger flows. There is no obvious scale at which this process terminates. The cosmic web extends across the entire observable universe, 93 billion light-years in diameter, and on that scale, the largest structures observable are only a small fraction of the whole. Laniakea, at 520 million light-years, is enormous by human standards and unremarkable by universal ones. What lies beyond Laniakea, then, is not emptiness. It is more structure, more flow, more mass concentrations pulling on each other across distances that make Laniakea itself look modest. The South Pole wall wraps around it. Shapley pulls on it from one direction. Perseus Pisces anchors a different gravitational basin nearby. The Cosmic Flows 4 catalogue has already pushed the frontier outward, and the catalogues that follow will push it further still. Every boundary we draw around our cosmic home turns out to have something larger just outside it. From far enough out, the universe looks like a net, not a metaphor, not a poetic approximation. When astronomers map the distribution of galaxies across hundreds of millions of light-years, the actual image that comes back looks like a three-dimensional mesh, bright filaments running between dense nodes, with vast dark holes where almost nothing lives. Superclusters sit at the intersections. Filaments run between them, and the space in between, most of the volume of the universe, is nearly empty. This is the cosmic web, and Laniakea is one small piece of it. The scale of the observable universe is roughly 93 billion light-years across. Laniakea spans about 520 million light-years. Do the math. Our entire supercluster, with its 100,000 galaxies and mass equivalent to 100 quadrillion suns, occupies less than 1% of the observable universe's diameter. Drop it into the full cosmic map, and it becomes difficult to find. The web extends in every direction, repeating its pattern of filaments and voids and dense nodes, all the way to the edge of what we can see. Laniakea is one node in that pattern. Nothing about its location is obviously special. Nothing marks it as unusual among the thousands of similar structures scattered across the cosmic map. The voids are the part that most people don't expect. When you picture the universe packed with galaxies, you are picturing the bright parts, the filaments and clusters. But the voids, those enormous dark regions between the filaments, are not exceptions to the rule. They are the rule. The voids dominate. A single void can stretch 100 to 300 million light-years across. Some of the largest, the supervoids, are even bigger. The density inside them is less than 1/10 of the average density of the universe. Galaxy after galaxy, cluster after cluster, essentially nothing for hundreds of millions of light-years in any direction. The universe, by volume, is mostly darkness. The bright web we trace is a thin skeleton stretched across an enormous emptiness. What makes this structure strange is that it was predictable. Scientists did not discover the cosmic web by looking at the sky and then scrambling to explain what they saw. They predicted it first, from the mathematics of gravity and the initial conditions of the early universe, and then confirmed it through observation. The Millennium Simulation, run in 2005 by a team including Volker Springel and hundreds of collaborators, started with conditions matching the early universe and ran gravity forward across 13 billion years of simulated time. The result was a filamentary web of structure that matched the observed distribution of galaxies with uncomfortable precision. Uncomfortable because nothing about the early universe looked like it was headed toward this. The early universe was almost perfectly smooth. Almost. Not quite. The temperature variations in the cosmic microwave background are tiny, 1 part in 100,000, but they were there, baked into the universe by quantum fluctuations in the first fraction of a second after the Big Bang. Inflation stretched those quantum variations to macroscopic scales. Gravity did the rest. Regions that were slightly denser than average pulled in more matter. Regions that were slightly less dense lost matter to their neighbors. Over hundreds of millions of years, the slight variations grew. Dense regions became filaments. The densest intersections of filaments became clusters and superclusters. The underdense regions became voids. The same process, operating on the same initial conditions, produces the same web pattern every time you run the simulation. The cosmic web is not accidental. It is the inevitable output of simple physics applied to a nearly uniform starting state. The Illustris simulation and its successor Illustris TNG pushed this further. These models incorporated not just gravity, but gas dynamics, star formation, black hole feedback, and the influence of dark energy. The resulting simulated universes looked, at large scales, almost indistinguishable from what we observe. Filaments in the right places, voids of roughly the right size, clusters of roughly the right mass. The match is not perfect. There are still open questions about the precise distribution of matter on small scales. But the broad architecture of the cosmic web has been reproduced repeatedly from first principles. This is one of the more remarkable facts in all of modern cosmology. The largest structures we can observe were written into the universe before the first star ever formed. Laniakea sits in this web the way any other supercluster does. It is a gravitational basin, a node where filaments converge and matter has pooled over billions of years. On the full cosmic map, at the scale where Laniakea becomes a recognizable object, dozens of similar structures are visible in every direction. The Shapley Supercluster, the Perseus-Pisces chain, the Hercules Supercluster, each one a basin like Laniakea, each one pulling its local collection of galaxies inward, each one connected to its neighbors by filaments and separated by voids. The cosmic web at this scale looks almost biological, dense nodes connected by thin, bright threads, vast, dark cavities in between. If you have ever seen an image of neurons under a microscope, or a leaf's vein structure, or the foam that forms when soap bubbles crowd together, those images all resemble the cosmic web for the same mathematical reason that different physical systems, driven by similar branching processes, tend to produce similar geometric patterns. There is nothing cosmologically remarkable about Laniakea's position in this web. It is not at the center of anything. It is not the most massive node within reach. It is one of many similar structures spread across a universe that extends unimaginably far beyond what any current telescope can probe. The only thing that makes Laniakea unusual is our location inside it. Because we are here, we can study it in detail that is impossible for any other supercluster. We know its shape, its mass, its internal flows, the positions of its major clusters, the behavior of its filaments. We have mapped it at a resolution no other supercluster will achieve in any telescope that currently exists. That is the advantage of being inside something, rather than looking at it from across the universe. Laniakea is one knot in that net, not special in any obvious cosmological sense, but the knot we happen to be able to examine from the inside. One of the earliest clues that something was pulling our region of the universe came not from counting galaxies, but from measuring temperature. In the 1970s, when physicists first mapped the cosmic microwave background in fine detail, they expected to find something close to uniform. The CMB is the afterglow of the Big Bang, light released roughly 380,000 years after the universe began, now cooled to just a few degrees above absolute zero, arriving at our detectors from every direction in the sky. If the universe were perfectly smooth, and we were sitting still relative to that background, the temperature would be essentially the same in every direction. It is not. One side of the sky runs slightly warmer. The opposite side runs slightly cooler. The difference is tiny, on the order of 1/1000th of a degree, but it is real, clean, and impossible to ignore. That asymmetry is called the CMB dipole, and what it tells you is motion. When you move toward a source of light, the waves compress slightly and shift toward higher energy, higher temperature. Move away, and they stretch, cooling down. The dipole in the CMB is a Doppler signature. Our entire region of the universe is moving fast, roughly 600 kilometers per second, relative to the background radiation that fills all of space. That number raised an immediate question. 600 kilometers per second is not slow. It is not something you can attribute to the gravity of a nearby galaxy cluster or even a modest supercluster. Something with enormous gravitational pull had to be responsible. And when astronomers tried to account for all the known mass in the local universe, all the visible galaxy clusters within a few 100 million light-years, they could not explain it. The pull of known structures was not enough. There was a missing source. That gap was one of the first signs pointing toward what would eventually be called the Great Attractor, the gravitational engine sitting near the center of Laniakea, pulling our local group and thousands of other galaxies toward a common point, hundreds of millions of light-years away. What made this early evidence particularly strange was that the bulk flow was not just ours. Individual galaxies nearby were showing anomalous velocities in the same general direction. Galaxy clusters across a wide region of space were all drifting toward the same part of the sky, faster than the cosmic expansion alone could explain. This is what peculiar velocities look like in practice. Not random noise scattered in all directions, but a coherent drift, a tide, millions of galaxies, all leaning the same way. The CMB dipole was the loudest signal, but the galaxy velocities were the confirmation that the effect was real and widespread. The problem with early peculiar velocity data was that it depended entirely on galaxy distance measurements that carry their own uncertainties. If your distances are slightly wrong, your inferred velocities are wrong. A pattern that looks coherent might dissolve under better measurements. Astronomers needed a way to check the velocity field independently, using a completely different physical process. That check eventually arrived in the form of a phenomenon called the kinetic Sunyaev-Zeldovich effect. Here is the basic picture. Galaxy clusters contain enormous clouds of hot gas, plasma at tens of millions of degrees, threaded through the space between individual galaxies. When CMB photons travel through this hot gas, they interact with the fast-moving electrons. If the cluster itself is moving relative to the CMB rest frame, this interaction leaves a subtle imprint on those photons. Moving toward us, the cluster slightly boosts the energy of passing photons. Moving away, it slightly reduces it. The effect is extraordinarily small. Detecting it requires precise microwave observations, careful subtraction of other signals, and large statistical samples of clusters. But it is physically distinct from anything in the galaxy distance measurements. No Tully-Fisher relations, no fundamental lane corrections, no distance ladder. Just microwave photons and hot gas and the Doppler shift of a moving cluster, read directly from the sky. When researchers began applying kinetic Sunyaev-Zeldovich measurements to galaxy clusters across the local universe, the results were striking. The clusters showed bulk motion, not random velocities pointing in scattered directions, but a coherent flow in roughly the direction of the Great Attractor, consistent with what the peculiar velocity surveys had been showing for decades. This was not a marginal overlap. The independent probe, built on entirely different physics, pointed toward the same gravitational basin that Tully's Watershed analysis had defined using galaxy flows. What this convergence means is important. A recurring concern whenever a large-scale structure gets mapped from peculiar velocities is that the result might be an artifact, a product of which galaxies happen to be measured. That surveys covered which parts of the sky, which distance methods were applied. Laniakea was defined using a specific catalogue of roughly 8,000 galaxies. That is a finite sample with finite coverage. If the pattern were statistical noise, independent probes using different physics on different objects should produce a different picture. They do not. The CMB dipole, the bulk flow studies of the 1980s and 1990s, The kinetic Sunyaev-Zeldovich measurements from large microwave surveys all describe the same motion across the same enormous volume of space. Multiple independent methods of measuring motion at cosmic scales now point toward the same picture: a coherent flow of galaxies across hundreds of millions of light years, converging on the same gravitational basin. We do not live near the heart of Laniakea. The Milky Way sits out near the edge, somewhere on the outer rim of a structure 520 million light-years across, pulled slowly but measurably toward the gravitational center. Slowly is the key word. The distance between us and the Great Attractor is somewhere between 150 and 250 million light-years. At our current infall velocity, reaching it would take far longer than the current age of the universe. And dark energy will almost certainly intervene before any arrival is possible. So we are falling inward, technically, but we are never going to get there. We are permanent residents of the outskirts. What would it look like to live somewhere else? Imagine the Milky Way had formed closer to the dense core of Laniakea, near one of the major clusters at the heart of the structure. The sky would look different in ways that are hard to fully picture. Galaxy density near the center is dramatically higher. Neighboring galaxies would be closer. Interactions and mergers between galaxies happen far more frequently in dense environments, and those collisions drive bursts of star formation, reshape spiral arms, heat the surrounding gas, and feed supermassive black holes into periods of intense activity. A galaxy in that environment would be a different kind of place, noisier, more active, more frequently disrupted. The quiet spiral structure of the Milky Way, which has remained relatively undisturbed for billions of years, is partly a product of where we ended up. The outskirts are calm. Out here, the galaxy density drops. In some directions, the voids open up, regions tens of millions or hundreds of millions of light years across, where almost nothing lives. These are not empty in an absolute sense, but the density of matter is less than 1/10 of the universe's average, and galaxies in voids are rare and isolated things. We have voids opening up around us in certain directions right now. The local group is not completely alone, but it is a small association of galaxies in a relatively sparse region, far from the nearest major cluster. That is just the reality of living on the periphery of a supercluster. The closest large cluster to us, the Virgo cluster, is still 50 to 60 million light-years away. In cosmic terms, that is a neighbor. In any other terms, it is an almost meaningless distance. There is something worth sitting with here. The fact that we ended up in this particular location, on the quiet edge rather than the turbulent core, is not a coincidence in the way luck is a coincidence. It is the outcome of processes that were set in motion almost 14 billion years ago. And this is where the story gets genuinely strange. The structure of Laniakea, the reason the Great Attractor exists where it does, the reason the Milky Way formed in the specific region of space it occupies, all of it traces back to conditions in the first fractions of a second after the Big Bang. The early universe was almost perfectly uniform. Almost. There were tiny fluctuations in density, variations so small that the temperature difference they created in the cosmic microwave background is measured in 100,000ths of a degree. These fluctuations were not random in the classical sense. They were quantum mechanical. At the smallest scales imaginable, quantum uncertainty produces unavoidable variations in energy density. In the very early universe, During the period cosmologists call inflation, space expanded so violently and so fast that those microscopic quantum fluctuations were stretched to cosmic scales. A variation that existed across a distance smaller than a proton became, after inflation, a variation spread across what would eventually be millions of light years. The universe locked those fluctuations in as it expanded. Gravity did the rest. Over billions of years, regions that were even slightly denser than average pulled in surrounding matter. The denser they got, the more they pulled. The emptier regions got emptier as matter drained away toward the denser ones. What started as a near-uniform gas of hydrogen and helium slowly organized itself into the cosmic web, filaments and clusters and voids, over timescales measured in billions of years. The Great Attractor, the dense concentration of mass at the heart of Laniakea, formed because gravity amplified a slight overdensity that had its origin in a quantum event that happened before a single atom existed. That is not a small claim. The reason the Milky Way is where it is, the reason we are on the outskirts of this particular structure rather than somewhere else, traces back to a quantum fluctuation that was inflated to cosmic scales before the universe was a second old. There was no inevitability to the specific location. If the fluctuations had been arranged slightly differently, the large-scale structure would have assembled differently. The Great Attractor would be somewhere else. The Milky Way would be somewhere else. The whole map changes with tiny differences in those initial conditions. We are here because of randomness that occurred at the very bottom of physical reality and was then enlarged to a scale of hundreds of millions of light years. This is not philosophy drifting away from the science. It is the science. Cosmologists can take the measured fluctuations in the cosmic microwave background, run them forward through simulations using known physics, and reproduce structures that look like the cosmic web we actually observe. The simulations produce filaments, voids, clusters, and superclusters in roughly the right proportions and at roughly the right scales. The structure is predictable. The specific arrangement is not. The quantum randomness of the earliest moments of the universe, amplified by gravity over 13 billion years, is what put us where we are, on the quiet edge of an immense heaven. If you wanted to write out where you live in the most complete way possible, the address would be longer than most people expect. Start with the obvious part. Earth, a rocky planet about 8,000 miles across, orbiting an average star roughly 93 million miles away. That star is the Sun, and the Sun sits inside a solar system that stretches roughly 4 to 5 light hours out to Neptune, and considerably further if you count the loose halo of comets at its outer edge. That whole region, every planet, every moon, every chunk of rock and ice that gravitationally belongs to our star, fits inside a bubble perhaps 2 light years across at its most generous estimate. That is your street address. A 2 light-year bubble in a cosmos 93 billion light-years wide. Step outward. The Sun is one of somewhere between 200 and 400 billion stars in the Milky Way galaxy. The Milky Way is a barred spiral, a flat rotating disk about 100,000 light-years across and roughly 1,000 light-years thick through much of its disk. The Sun sits about 26,000 light-years from the galactic center, out in one of the spiral arms, in a fairly quiet and unremarkable neighborhood. The solar system is so small compared to the Milky Way that if you shrunk the galaxy to the size of North America, the entire solar system would be smaller than a dime. The Milky Way is your city, and it is already almost incomprehensibly large. But the Milky Way is not alone. It belongs to a collection of galaxies called the Local Group, a gravitationally bound cluster of roughly 80 known galaxies spread across approximately 10 million light-years. Most of these 80 galaxies are small. The dominant members are the Milky Way and Andromeda, two large spirals falling toward each other at several hundred kilometers per second, expected to collide in about 4 billion years. The Local Group is your region, your county, if you're keeping the metaphor running. 10 million light-years is 100 times the width of the Milky Way. Hold that ratio in your head, because it is about to repeat itself. The Local Group is one small cluster among many in the Virgo Supercluster. This structure, which astronomers had considered our home supercluster for decades before 2014, stretches roughly 100 million light-years across. It contains something on the order of 100 galaxy groups and clusters. The Virgo cluster itself, a dense concentration of several thousand galaxies, sitting roughly 50 to 60 million light-years from the Milky Way, anchors the structure. The Virgo Supercluster is 10 times wider than the Local Group. Each step outward in this address multiplies the scale by a factor that should feel staggering, but somehow keeps arriving as a routine number in the equations. This is part of what makes cosmic scales genuinely difficult. The jumps are not gradual, they are sudden and enormous. And then there is Laniakea. The Virgo Supercluster, it turns out, is not a standalone structure. It is one subdivision, one lobe, of Laniakea, the supercluster defined in 2014 by tracing the gravitational flow of galaxies rather than just their density. Laniakea stretches 520 million light-years across. It contains roughly 100,000 large galaxies. Its total mass is something in the neighborhood of 10 to the power of 17 solar masses, which is 100 quadrillion suns, a number that stops being a number and becomes a symbol. The Virgo Supercluster, which felt enormous when it was considered the top of the hierarchy, is approximately 1/5 the width of Laniakea. What we called the largest structure we belonged to was a suburb, a small neighborhood in something vastly larger that nobody had successfully outlined until fairly recently. Beyond Laniakea, the address continues. The Great Attractor at Laniakea's center is itself moving toward the Shapley Supercluster, several hundred million light-years further out. Laniakea is likely part of the Pisces-Cetus supercluster complex, a structure so large it dwarfs even Laniakea. The South Pole wall wraps around Laniakea's edge like an arm. These structures together form part of the cosmic web, the large-scale architecture of the observable universe. Filaments of galaxies hundreds of millions of light-years long, connecting nodes like Laniakea, surrounding voids up to 300 million light-years across, where almost nothing lives. The full observable universe spans roughly 93 billion light-years. Laniakea, at 520 million light-years, represents less than 1% of that diameter. The challenge of communicating all of this is real. The human mind handles a few orders of magnitude comfortably. It can picture a city being larger than a neighborhood, a country being larger than a city. But the jump from the solar system to the Milky Way is a factor of roughly 1 billion in linear scale. The jump from there to Laniakea is another factor of 5 million. These are not differences in degree. They are differences that exhaust the imagination. It is the same problem physicists face when trying to hold atoms and solar systems in the same mental picture simultaneously. The scale range is simply too large for intuition to carry without breaking. What astronomers mean when they talk about a cosmic address is something genuinely new in human history. For most of our existence as a species, the question of where exactly we sat in the universe had no real answer. The sky was overhead. Beyond that, the answers were stories. Even 100 years ago, astronomers were still debating whether the Milky Way was the entire universe or just one of many island galaxies. The idea that those galaxies organized into groups, clusters, and superclusters came later. The idea that those superclusters were themselves components of even larger basins of gravitational attraction came later still, in 2014, in a paper in Nature. Each generation has extended the address by one more line. This is not trivia. It is the most complete answer to the question of where we are that any human civilization has ever been able to give. Dark energy is the reason Laniakea will not survive. That sentence sounds dramatic, but it is just physics. To understand what it means, you have to understand what dark energy actually is. And the honest answer is that nobody fully does. What astronomers know is this: dark energy is the dominant energy component of the universe, accounting for roughly 68% of everything. It does not clump. It does not interact with light or matter in any detectable way. It is invisible, massless, and spread perfectly uniformly across all of space. The only thing it appears to do is cause space itself to expand, and it does this with a persistence that nothing in the universe can overcome at large enough scales. For most of the 20th century, physicists assumed the expansion of the universe was slowing down. This made intuitive sense. The Big Bang flung matter outward. Gravity pulls matter together. Over time, gravity should gradually win, decelerating the expansion, the way a ball thrown upward gradually loses speed. The only real question was whether gravity would win completely, stopping the expansion and reversing it into an eventual collapse, or whether the universe would expand forever at a diminishing rate. Both options assumed the same direction: expansion slowing over time. Then, in 1998, two independent teams of astronomers studying distant Type 1a supernovae published results that were almost impossible to believe. The supernovae were fainter than they should have been. They were farther away than the models predicted. The expansion was not slowing down, it was speeding up. Space was not fighting gravity to a standstill. Something was actively pushing it apart faster with every passing era. That discovery earned its lead researchers the Nobel Prize in Physics in 2011, and it rewrote cosmology in a single year. The force responsible for this acceleration is what physicists called dark energy, a label that carries a lot of honesty in it. The word dark here means unknown. It is not dark matter, which at least has well understood gravitational effects. Dark energy is stranger than that. It behaves like a property of empty space itself, a baseline energy that the vacuum carries, sometimes called the cosmological constant, a term Einstein introduced and then famously abandoned and then turned out to be correct about after all. As space expands, a new volume of empty space is created. The total amount of dark energy grows with it. This is why the expansion accelerates over time, rather than settling into a constant rate. More space means more dark energy. Which drives more expansion? Which creates more space? The feedback loop is slow by human standards, but relentless on cosmological timescales. Now here is where Laniakea enters the picture. Gravity and dark energy are in a continuous contest, and which one wins depends on scale. On small scales, gravity wins easily. The atoms in your body are not being pulled apart by dark energy. Planets, solar systems, galaxies, even galaxy clusters, these are all gravitationally bound. The matter in them is locked together tightly enough that the gentle outward pressure of dark energy is irrelevant. But as you move to larger and larger scales, gravity becomes weaker and dark energy becomes more significant. Superclusters occupy exactly the zone where this contest becomes interesting. Laniakea is not gravitationally bound. This was established when it was first defined in 2014, and it is worth sitting with. The structure is real. The galaxy flows are real. The inward motion toward the Great Attractor is real. The basin of attraction exists, but the outer regions of Laniakea do not have enough gravitational connection to the center to resist the expansion of space indefinitely. The Great Attractor exerts a genuine gravitational pull, estimated at roughly 10 million billion solar masses of influence. That sounds enormous. Against dark energy operating across 500 million light-years, it is not enough. The outer galaxies of Laniakea are already in a kind of slow tug-of-war. Right now, for our epoch of cosmic history, the gravity of the Great Attractor remains strong enough to draw our local group and billions of nearby galaxies toward its basin. This infall will continue for billions of years. But the boundary of that influence is not fixed. As the universe expands and the distances between outer regions of Laniakea and its gravitational center grow, the gravitational force between them weakens. Dark energy's push does not weaken with distance the way gravity does. So the balance tips. Galaxies near Laniakea's periphery will eventually cross a threshold where expansion carries them away faster than gravity can draw them back. The filaments at the edges will thin. The outer clusters will drift. The structure will not collapse or explode. It will simply dissolve gradually and quietly over timescales that are hard to write down meaningfully. What does the far future universe actually look like? Astronomers have modeled this, and the picture is striking in its emptiness. The local group itself, the Milky Way, Andromeda, and roughly 80 smaller companions, is bound. In several billion years, the Milky Way and Andromeda will merge into a single massive galaxy. That merged structure will remain gravitationally locked. But beyond the local group, the rest of Laniakea will gradually recede. The Virgo cluster will eventually pass beyond the boundary where gravitational connection is possible. The Hydra and Centaurus clusters, the Norma cluster, the hundreds of groups that today participate in the infall toward the Great Attractor, all of them will drift beyond reach. On timescales of hundreds of billions of years, what remains will be isolated islands of gravitationally bound matter, separated from each other by expanding voids that grow wider with every passing eon. The universe will still exist. Stars will still burn for a while. But the large-scale structure we can see today, the filaments, the clusters, the flowing basins of attraction, the shape that Brent Tully's team mapped in 2014, none of that will be visible. An observer in that far future universe, looking outward from whatever remains of our local group, would see nothing but darkness in all directions. No neighboring galaxies close enough to identify. No structure at all. The cosmic web will have stretched beyond any possible detection. Whatever civilization existed then would have no way of knowing that a supercluster had once surrounded them. 500 million light-years of galaxies flowing together in a coherent structure with a name that meant immense heaven. In the far future, nothing observable will remain to show that hundreds of thousands of galaxies once flowed together toward a common center across 500 million light-years of space. The 2014 paper that named Laniakea was not the end of the story. It was more like the first reliable map of a territory that had previously been described only in rumors. Tully's team had used a catalogue of roughly 8,100 galaxies with measured distances and velocities. That number sounds large. For a structure 520 million light-years across, it is actually quite thin coverage, like trying to map an entire continent from a few hundred survey points scattered unevenly across it. The researchers knew this. The paper itself acknowledged the gaps. What they had produced was a framework, a first outline, and the work of filling it in had barely started. Cosmic Flows 3 came next. Released in 2016, it pushed the galaxy count to around 18,000. More galaxies meant denser sampling, which meant the flow patterns could be traced with finer resolution. The boundaries of Laniakea didn't collapse under the new data. The basic shape held, but the details shifted. Some filaments resolved more clearly. Some previously ambiguous regions near the edges snapped into focus. The watershed boundaries, which in the original paper had been somewhat blurry in certain directions, tightened in some places and softened in others. This is how science actually works. Not a single revelation, but a slow accumulation of better measurements, each one adjusting the picture slightly. The 2014 map wasn't wrong. It was coarse. Then Cosmic Flows 4 arrived in 2023, and the number jumped to nearly 56,000 galaxies. That is roughly 7 times the original dataset. 8 different distance measurement techniques fed into the catalogue: the Tully-Fisher relation for spiral galaxies, the fundamental plane for ellipticals, and several others, all cross-checked against each other. The result was a peculiar velocity map of the local universe with a level of detail that would have been unthinkable in 2014. The 2023 analysis confirmed Laniakea's overall size and shape. 520 million light-years across, roughly 100,000 large galaxies, mass sitting around 10 to the 17th solar masses. The original outline held, but the same watershed technique that had defined Laniakea in 2014 now revealed 5 neighboring superclusters in comparable detail: Shapley, Perseus Pisces, Hercules, Lepus, and Apus, each one its own basin of gravitational attraction, each one adjacent to Laniakea in the larger cosmic web. The local universe suddenly had neighbors with names and borders. There are debates, though. Not everyone agrees that Laniakea's boundaries are drawn in exactly the right places. Some researchers argue that the edges of the structure are sensitive to which galaxies are included in the catalogue, and how distances are weighted at large radii. The Zone of Avoidance still creates real gaps in the data. Galaxies behind the Milky Way's disk are underrepresented in every version of Cosmic Flows, which means the flow maps in those directions are less reliable. If significant structures are hidden in those gaps, the boundary of Laniakea in that region of sky could shift when better data eventually fills the blind spot. These are not fatal objections. They are exactly the kind of edge case uncertainties you expect at the frontier of a measurement campaign. The core of the structure is solid. The edges are still being negotiated. What comes next is more data, orders of magnitude more. Spectroscopic surveys now underway or in planning will measure galaxy redshifts for tens of millions of objects. The Dark Energy Spectroscopic Instrument, already operating in Arizona, is accumulating galaxy spectra at a rate that would have seemed impossible a decade ago. Surveys like these won't just extend the cosmic flow's approach, they will transform it. Peculiar velocity maps derived from millions of galaxies, instead of tens of thousands, will resolve structures that currently appear as vague suggestions in the data. The flow patterns around Laniakea's edges, where the supercluster's influence fades and the influence of neighboring structures takes over, will become far clearer. The extremely large telescope, currently under construction in Chile's Atacama Desert, will add something different. Its light-gathering power is so far beyond existing instruments that it will be able to measure distances and velocities for galaxies that are simply too faint for current surveys to handle reliably. This reaches further out and fills in the picture at larger scales. Weather structures like the South Pole Wall, the enormous arc discovered in 2020 just beyond Laniakea, connect to Laniakea's flow patterns or belong to entirely separate basins is exactly the kind of question that next-generation instruments are positioned to answer. The map of our cosmic neighborhood is not finished. That might sound like a limitation, but it is also the honest state of things. And it means the most interesting results may not be the ones already published. Every time the catalogue has expanded, something unexpected has appeared at the new resolution. More galaxies revealed cleaner filaments. Better coverage revealed neighboring superclusters that the original data could only hint at. There is no obvious reason to expect that pattern to stop. The outline that Tully's team drew in 2014 has held up, but the details inside it are still being filled in, and the territory just outside it keeps turning out to be larger than anyone expected. Every civilization that ever looked up at the sky had some answer to the question of where they were in it. The Babylonians placed themselves beneath the dome of gods. Medieval astronomers put Earth at the center of nested crystalline spheres. Polynesian navigators read the sky not as theology, but as a map, and they used it to cross the largest ocean on the planet without instruments, without landmarks, without anything except an extraordinarily precise knowledge of the heavens above them. Every one of those civilizations had an answer. None of them had the right one. We are the first generation in human history that does. That answer is strange enough to stop you cold if you sit with it. You are not at the center of your galaxy. You are not at the center of your galaxy cluster. You are not at the center of your supercluster. The Milky Way sits near the outer edge of Laniakea, in a relatively quiet, relatively sparse region, far from the dense clusters where galaxy interactions are frequent and the cosmic environment is violent. We are on the rim. We are in the suburbs of an immense structure that stretches 520 million light-years from one side to the other, and we are being slowly pulled toward its heart by a gravitational concentration so massive it took decades just to find it. That pull will never complete. Dark energy will likely win before we get anywhere near the center. We are drifting outward, even as we fall inward, passengers in a structure that is quietly dissolving at its edges. And yet this unremarkable outpost is the only place as far as anyone knows, where the question has ever been asked. That asymmetry is strange. The Great Attractor sits at the gravitational heart of Laniakea, surrounded by some of the densest concentrations of galaxies in our cosmic neighborhood. Nobody there is asking anything. The rich clusters of the Norma Supercluster region, the dense nodes where filaments converge, silent. The vast empty voids that occupy most of Laniakea's volume, silent. One minor spiral galaxy, far from anything particularly remarkable, produced the only observers in the known universe who looked outward and wanted to understand the structure they were part of. That is not an answer to anything. It is just the fact, and the fact is strange. Think about what Tully's team actually did. The Polynesian navigators used the sky to find their place in the ocean. They read the stars, the swells, the flight paths of birds, and they triangulated themselves into a location. Tully's team did something that rhymes with that, but runs deeper. They didn't use the sky to find their place in the world. They used the motion of 100,000 galaxies to find their place within the structure that contains the sky itself. The navigators crossed the Pacific. The astronomers mapped the Pacific and discovered it was part of a continent they hadn't known existed. The Hawaiian Name connects those two acts across centuries. The same language, the same sky, an entirely different scale of understanding. What that understanding gives us is a complete address. Not just Earth, not just the solar system, not just the Milky Way or the local group, but the full hierarchy extending outward to Laniakea and beyond. For most of human history, that address was unknown past the level of a few nearby stars. A century ago, we didn't know other galaxies existed. 50 years ago, we didn't know what was pulling our region of the universe off course. 10 years ago, we didn't have a name for the supercluster we live in. The discovery is genuinely recent. The picture is genuinely incomplete. There are structures beyond Laniakea still being traced, boundaries still being debated, catalogues being extended from 8,000 galaxies to 56,000, and eventually further still. The 2014 paper was a door opening, not a door closing. What sits on the other side of that door is uncomfortable and astonishing in equal measure. We are peripheral. We are temporary, in the sense that the structure we belong to will not survive on cosmological timescales. The outer filaments of Laniakea are already losing coherence to dark energy. In hundreds of billions of years, the flows that define our cosmic home will disperse into an expanding void. Laniakea will not exist in any meaningful sense. The immense heaven will dissolve. This is not a reason for distress. It is just the physics. The structure was real. The flows were real. The answer to where we are is real, even if the structure itself is temporary. Somewhere on the outer rim of an immense heaven, there is a small spiral galaxy, and on one of its unremarkable arms, something learned to ask where it was, and is only now beginning to find out.